In this video, I am going to learn about EIP-712. The end goal is to implement typeHash, domainSeparator, struct build EIP-712 verifier, smart contract with Foundry tests, and then push that to the copy trade vault GitHub repo. So this is the learning objective for today, and the learning outcome or process that I am following is I am using a plan executor whose description is continuous upscaling, and inside this I have set the instructions to be. I have asked the AI to be my tutor and learning coach. The goal is not to teach me by giving answers, but the goal is to help me develop deep understanding through guided learning, questioning, deliberate practice and verification. I'll paste the instruction in the description of the YouTube video, but this is how today I am going to learn and use AI as my personal mentor and tutor. So let us get started. How can I help you today? I'll go to the learning objective. So this is the deliverable. I'll copy this and paste it over here. Now let us wait for a guided approach from AI. So before we dive into EIP-712 and building EIP-712 verify.soy, so let me understand where you're starting from. This helps me guide you effectively rather than waste your time on things you already know, or worse, skip foundations you actually need. So the first question is, in your own words, what do you think EIP-712 is trying to solve? My own words, EIP-712 is trying to solve the problem of signing data from arbitrary hex strings to meaningful human readable or understandable context by signing the data. Okay. So the core motivation is making signed data human readable rather than opaque hex blobs. Before EIP-712 existed, wallets like MetaMask would show users something like sign this message. Based on what you just said, what specific danger does this create for a user? So if a user gets only this message, that is sign this message, and opaque X blobs, what dangers does this create for a user? The dangers can include stealing users' funds, making user approve to spend tokens to the attacker's wallet, which the attacker can later on use to move funds from user wallet to any other destination. Good instincts, you are thinking in the right direction, but I want you to push you a little bit deeper. Those are consequences. Let me ask about the mechanism. You said an attacker could make a user approve to spend tokens. If a user signs an arbitrary hex blob, how does the attacker actually use that signature? What does a signature prove on chain? And why does an opaque hex blob make that dangerous? Think about what ecrecover does and what a smart contract actually checks when it receives a signature. take your time. What's your intuition here? First, what does a signature prove on chain? It proves ownership. And why does an opaque hex blob make that dangerous? Because the opaque hex blob can have data which represents transferring users ETH balance or any other token balance. When a smart contract receives a signature, it basically checks the address with, say, message.sender or owner of token ID in case of NFT, or balance of message.sender in case of ERC20. Now these can be used to get away with users' FUTs. You said a signature proves ownership and that a contract checks it against. Okay, when a contract calls ecrecover hash VRS, what exactly does it get back? When a contract calls, when a contract calls ecrecover, it gets back the address that has signed the hash. It may or may not be same as message.sender. Right. So ecrecover returns the address that signed the hash, and yes, it may or may not be message.sender. Now this is the critical insight. I want you to arrive at yourself. Question: if ecrecover returns the address that signed the hash and the user blindly signed an opaque hex block, who constructed that hex block? And therefore who controlled what message the user was actually signing? What does that mean for what the contract will believe the signer authorized? And the user blindly signed an opaque hex block. Who constructed that hex block? That hex block can be constructed on the server or on the front end by the attacker, and therefore who controlled what message the user was actually signing? The attacker controlled what message the user was actually signed. What does that mean for what the contract he believed the signer authorized? The contract believes code is law and it has no way of figuring out who created the hex blob and was the message signed is indeed what was needed by the user. Okay, The attacker constructs a hex blob representing a malicious action. The user sees gibberish and signs it. ecrecover confirms the user signed it. The contract believes the user authorized the action. The contract has no way to know the user was deceived. This is called a blind sign-in attack. Okay. Now you understand the problem. One more question before we look at EIP-712 solution. EIP-712 makes the data human readable in the wallet, but human readability alone isn't enough to fully solve this. Consider this scenario. The user is on legitdap.com. They sign an EIP-712 message. An attacker replays that exact same signature on evildap.com, which has a contract that accepts it. What second problem does EIP-712 need to solve beyond just human readability? I think I know this answer. It should solve signature replay mechanism, signature replay attack. And for that, EIP-712, I guess, uses chain ID or Nonce. Chain ID is used to protect signature replay attacks across different blockchain network, and Nonce is used to protect on the same blockchain network. Okay, chain ID and Nonce code. EIP-712 actually bakes several pieces of identifying information into every signature. You got two of them. Beyond chain ID and Nonce, what other pieces of information would you want baked into a signature to uniquely identify which contract and which application the user is signing for? Think about this scenario. Two different dApps on the same chain. Both have a transfer address to amount function. A user signs a message of dApp A. Could that signature be replayed on dApp B? What would prevent that? Okay, two different dApps on the same chain. Both have transfer. A user signs a message for dApp A. Okay, what would prevent that? Having address to explicitly in the message would prevent that, because dApp A will have dApp A and dApp D will have independent addresses. Okay, you start having address to in the message would prevent it, but address to is the recipient of the transfer. That's the destination of funds, not the identity of the dApp. Let me reframe the question. If dApp A is deployed at 0xAAA and dApp B is deployed at 0xBB, both accept the same signature format for transfer. A user signs a message intended for dApp A's contract. What single piece of information, if baked into the signature, would make that signature only valid for dApp A and rejected by dApp B? You already know this exists in Solidity. Every contract has one. What single piece of information, if baked into the signature, would make that signature only valid for dApp A and rejected by dApp B? You already know this exists in Solidity. Every contract has one. What single piece of information, if baked into the signature, would make that signature only valid for dApp A and rejected by dApp B? What could be the answer for this? You already know this exists in Solidity. Is it the forgraph function? Receiving unexpected calls, not about identity. Let me give you a smaller hint. You said it yourself a moment ago. That A is deployed and that B is deployed. Every contract has a unique identity on the blockchain. What is that identity for? Deployed contract address. Okay. If you bake the contract address into the signature, a signature intended for 0xAA will always fail verification on 0xPV. So let's now collect everything you have figured out on your own. A signature needs to bind to chain ID. So this prevents replay across chains. Contract address prevents replay across contracts on the same chain. Nonce prevents replay of the same action twice. The actual data human readable, so users know what they are signing. Now here's the key question before we look at the specification. EIP-712 bundles chain ID, contract address, and a few other fields into one special hash called the domain separator. Why do you think they separated it into its own hash rather than just throwing everything into one big flat hash? Think about gas costs and how often each piece of information changes. I'm not sure. I'm not sure. Maybe having a look at the documentation will clear this up. Let me look at the documentation and get back to Zoom. So here is EIP-712. So let me search domain separator. So what does a domain separator do? Oh, domain separator, encode domain separator. Okay. Here we have the definition of domain separator. Domain separator domain separator is equal to hashStruct EIP-712 domain, where the type of EIP-712 domain is a struct named EIP-712 domain with one or more of the below fields. Protocol designers only need to include the fields that make sense for their signing domain. Unused fields are left out of the struct type. Name the user readable names of signing domain, that is the name of the DApp or the protocol. The current major version of the signing domain. Signatures from different versions are not compatible. Okay, chain ID. The user agent should refuse signing if it does not match the currently acting chain. The address of the contract that will verify the signature. The user agent may do contract specific phishing prevention. And Byte's 32 salt, a disambiguating salt for the protocol. This can be used as a domain separator of last resort. So future extensions to this standard can add new fields with new user agent behavior constraints. User agents are free to use the provided information to inform or warn users or refuse signing. DApp implementers should not add private fields. New fields should be proposed through the EIP process. Field should be the order as above, skipping any absent fields. Okay, come after the above. User agent should accept fields in any order as specified by the EIP-712 domain type. Let's go back. EIP-712 bundles chain ID, contract address, and a few other fields into one special hash called the domain separator. Why do you think they separated it into its own hash rather than just throwing everything into? Okay. Separation is done mainly because of to increase readability when user signs a message, because it includes fields such as name, version, chain ID, verifying contract, and sort. Thus, they are separated. But why they are separated? This doesn't answer the question. I think the reason for separation would be to have user sign only the required hash and not what is not required, because domain separator acts or increases the readability from user's perspective during sign. Okay, you are circling around the answer, but I want to push you to the specific technical reason. You mentioned these fields change at different rates. Chain ID, verifying contract, name, version never changes after deployment. The actual message data changes with every single transaction. If domain separator never changes after deployment, where could a smart contract store it to avoid recomputing it on every transaction, and what does that see? If domain separator never changes after deployment, a smart contract would save that to a state variable and that will save bytes 32 hash. Okay, store it once in a state variable at deployment, never recompute it again. Now connect the dots. If everything was one big flat hash, domain fields plus message data together, could you pre-compute and cache it? Why or why not? If everything was one big flat hash, domain fields plus message data, could you pre-compute it and cache it? I think no, because hash is one way and from the hash cannot get the input back. And that's not quite the reason here. The message data, like calls for, changes with every transaction. If you combined domain fields plus message data into one single hash input, even though the domain fields never change, would the final hash ever be the same twice? No. The final hash will never be the same twice. So if they were combined into one flat hash, you would have to recompute the entire thing every single transaction, even though the domain fields never change. But by separating them, domain separator computed once at deployment, cached in a state variable, struct hash computed per transaction only the changing data, final hash just KChat 256 of domain separator plus struct hash, you save recomputing the domain portion on every single call. So the real reason for separation is gas optimization. Cache the static part, only compute the dynamic part per transaction. Plus the readability benefits you mentioned earlier, both are true. Now you have a solid mental model of why EIP-712 is designed the way it is. You understood it from first principles. Before we read the actual specification, tell me in your own words, what are the three components EIP-712 combines to produce the final hash that gets signed? Three components. Okay, so first, let me check that. Okay, definition of type, structure, specification. domain separator. So what does it combine? Type structured data. To define the set of all structured data, we start with defining acceptable types. Definition. Okay, before, what are the three components EIP-712 combines? It combines hashStruct. What is hashStruct? The hashStruct function is defined as ecrecover hash of typeHash with the encodeData. Or typeHash is this. The typeHash is a constant for a given struct type and does not need to be runtime computed. Okay. First hashStruct is this. And secondly, encode the type of a struct is encoded as name, where each member is written as, for example, so it has, okay, simple words, it has hashStruct, domainSeparator, and at last encodeData. The data to be encoded and signed, domainSeparator, the static part that differentiates different dApps on chain, different tabs, or okay, that's good, but I want to make sure you understand it, not just recall it. Let me test that. You wrote hashStruct. What is typeHash actually representing in plain English? Not the formula. Tell me conceptually what information does typeHash capture and why does it need to be included in hashStruct? Let me check what does typeHash capture. TypeHash is a constant for a given struct type and does not need to be runtime. Okay. So typeHash is a constant for a given struct type and need not be computed during runtime. Given struct type and does not need to be runtime computed. But you haven't told me what it represents. Let me ask it differently. Consider these two structs. Struct transfer address to uint256 amount and permit owner spender value. Both could have identical field values in some case. For example, both could encode to the same bytes if the addresses and numbers happened to match. Without typeHash, could you tell these two structs apart just from their encoded data? What does typeHash actually bind the signature to? Does typeHash, will I know that? Hash, what is code? Okay, so I think answer is here. TypeHash is equal to ecrecover256 hash of encode type then type of s. Without typeHash, could you tell these two structs apart just from their encoded data? So what basically typeHash does is it calculates ecrecover256 hash, then encodeType, then at last type of S. So by this definition, I'm assuming this definition gives the type hash. However, let me search for type of most type. Okay, to equal as long as type of is with type of v. Okay, here it is. We have the rationale for type hash. And the type hash is designed to turn into a compile time constant in Solidity. Okay, check 256 hash of. Then we have the struct name and its parameters. So from the type hash, several alternatives were considered and rejected for the reason. Use ABI-v2 function signature. Bytes 4 is not enough to be collision resistant. Unlike function signatures, there is negligible runtime cost incurred by using longer hashes. Alternative third was ABI-v2 function signature modified to be 256-bit. 256-bit ABI version 2 signatures extended with parameter names and struct names. The mail example from above would be encoded as mail person string name. Okay, from person string name address wallet to string content. This is longer than the proposed solution, and indeed the length of the string can grow exponentially in the length of the input. Okay, it also does not allow a recursive struct type. Include NatScript documentation. This would even more semantic information in the schema hash and further reduces chances of collision. It makes extending and amending documentation or breaking changes, which contradicts common assumptions. It also makes the schema hash mechanism very verbose. Got it. The type hash gives this definition gives the type hash. Without type hash, could you tell these two structs apart just from their encoded data? Or does type hash actually bind the signature to? Okay, the definition without type hash, no. It binds the signature to the structure data that the user has signed. Okay, you said it binds, but what? But look at what gets hashed to produce type hash. What two strings? Okay, transfer address to this. This is a string representation of the struct. What two things does this string capture that distinguish one struct type from another? What two things does this string capture? Address and amount. You said it binds to the structure data, but look at what gets hashed to produce type hash. Those are the field values, but look more carefully at the string itself. What comes before the parenthesis and what's inside? Is it just the values or something more? Okay, before the parenthesis is the structure name, and inside are the structure numbers. So this way, type hash distinguishes different structures. Okay. So typeHash binds the signature to the structure name, transfer versus permit, and the field names and their types. This means even if two structs have identical encoded data values, the typeHash will be different because their shape is different. Now let's put all three components together. You mentioned the final hash in EIP-712 is check 256 domain separator or hashStruct. What is the OR symbol representing here? And there's actually a prefix added before these two components in the final hash. Do you know what it is and why it exists? Why it exists? Look at how each signed type data constructs the final bytes before hashing. Okay. The sign method calculates an Ethereum specific signature with sign. This is the prefix x9 x01. Hash struct as defined above. Note the address to sign with must be unlocked. Type data, type structure data to be signed. Types properties. Okay. Data. Paramphystis, types, name, version, type. This is the result. There also should be a corresponding personal sign type data method which accepts the password for an account as the last argument. Okay. So the OR sign represents concatenation, and there's actually a prefix. Prefix is, but I don't know why it exists. Do you know what it is and why it exists? Look at how each signed type data constructs the final bytes before hashing. I think this is Ethereum related. Okay, what is the importance of prefix in the EIP-712? Prefix is a critical safety mechanism that guarantees a signed message can never be accidentally or maliciously submitted as a valid executable on-chain transaction. Let us look at the AI mode. Okay, 0x9 byte transaction isolation, malicious replay prevention. Raw Ethereum transactions are formatted using RLP. The safeguard: valid RLP encoded Ethereum transactions can never begin with byte 0x19. Okay, the result: by forcing the message to start with 0x9, the EVM guarantees that the signed data can never be accidentally or maliciously submitted to the network as a live executable transaction. Then 0x01 byte version specification. ERC-191 defines the byte immediately following 0x19 as the version time. 0x45 or E used for personal sign, it prefixes data with x19 Ethereum signed message. 0x00 used for data that contains a specific intended validator address. The final digest construction: when you sign an EIP-712 message, your wallet cryptographically signs a final 32-byte kcheck 256 hash formatted exactly like this. Okay. Without X901 anchor prefix, standardizing secure human readable signature across wallets like MetaMask would be impossible without risking significant cross-protocol security exploits. Okay. So I haven't understood it completely. So let's ask AI. 0x19 byte transaction isolation and 0x01 is the version specification. And why do we use it? By forcing the message I have referred to this from Google. Help me understand this. You found the answer, but you want to understand it, not just recall it. That's exactly the right instinct. Let me help you build the intuition from scratch. First, a foundational question. A raw Ethereum transaction, the kind that moves ETH or calls the contract, when it gets serialized for signing, what encoding format does it use? It uses RLP, recursive length prefix. It uses RLP, recursive length prefix. Ethereum transactions are RLP encoded. I want you to arrive at RLP encoding. When it encodes the list, always starts with a byte in the range 0xC0 to 0xFE. And when it encodes a short string, it starts with a byte in the range 0x00 to 0x7F or 0x80 to 0xV7. Can an RLP encoded value start with 0x19? Take a moment and think about what this means for a message prefixed with 0x19. Okay, when it encodes a list, it always starts with a byte. When it encodes a short string, it starts with a byte in the range. Can an RLP encoded value ever start with 0x19? Short string list. Take a moment and think about what this means for message prefixed. The message prefixed with 0x9 implies there are no lists or short strings. Exactly, 0x19 falls outside all valid RLP starting byte ranges. So a message starting is 0x19 can never be a valid RLP encoded Ethereum transaction. Okay. This means a signature over a message prefixed with 0x19 can never be reused as a valid transaction signature. Wow. The two signature spaces are permanently separated. Now the 0x01 byte after 0. Okay, so the key learning over here is the prefix including the byte 0x19. It falls outside all valid RLP starting byte ranges. So a message starting with 0x19 can never be a valid RLP encoded Ethereum transaction. Hence, even if nobody can use a signature as a Ethereum transaction data. Now the 0x01 byte after 0x19, you found that it represents version specification. But think about it this. EIP-712 is not the only EIP that uses the 0x19 prefix. EIP-191 defines the overall standard for signed data and different version exists. 0x00 data with intended validator, 0x01 structured data, that is EIP-712, and 0x45 personal sign. Why is having a version byte useful here? What problem would occur if all these different signing formats used just 0x19 with nothing after it? So what problem would occur? Problems like signature separation. Not able to understand. Okay. If the version is not specified, then it will become impossible to handle this inside the smart contract. Then it will become impossible to handle this inside the smart contracts, because smart contracts are deterministic and cannot execute dynamic code. Okay, the determinism point is true, but the core problem is simpler than that. If two different signing formats both start with just 0x19 and nothing else, could a signature intended for EIP-712 structured data be replayed against a contract expecting EIP-191 personally signed? Yes, it can be replayed. In both the cases, ecrecover will return the address, not sign the message. Okay, without the version byte, ecrecover happily returns a valid address in both cases. It has no idea which format was intended. A signature meant for one format could be accepted by a contract expecting a different format. The version byte 0x01 creates permanent separation between signing formats. A contract verifying EIP-712 signature knows it must see X19, X01, anything else is rejected before even calling ecrecover. So now you fully understand the final hash construction. Every piece has a purpose you derived yourself. X19 can never be a valid RLB transaction because X19 falls outside the valid RLP encoding ranges. Hence, you cannot use a message as a transaction. And X01 identifies this as EIP-712 structured data. Domain separator, it binds to this specific contract and cheat. And hashStruct binds to this specific struct type and data values. You now have a strong conceptual foundation. Before we move to implementation, one final question. In your own words, when a smart contract calls ecrecover on an EIP-712 hash and gets back an address, what exactly has that address holder proven? That address holder has proven that he or she has signed the data and gets back an address. What exactly has that address holder proven? That address holder has proven that he or she has signed the data. What specifically has that address holder proven? They agreed to consider all four components we just discussed. Don't just say sign the data. What exactly did they sign and what does that prevent? Okay, what exactly did they sign? Board set को कहते sign. They signed the EIP-712 typed data. What exactly did they sign and what does that prevent? They signed the EIP-712 typed data. Their signature cannot be replayed across different contracts because of the prefix X01 and X19 ensures their signature cannot be used as Ethereum transactions. Okay, saying they have, here we have considered the structured data, that is EIP-712 typed data, then prefix 0x01, ensuring that signature cannot be replayed across different contracts, because x01 ensures that the version part and x19 ensures that signature cannot be used as Ethereum transactions. And apart from that, what were the two other components? Domain separator is domain. They have signed for a specific DAB domain separator, and at last they have signed specific structured data, which is typeHash. Okay, the address holder has proven that they deliberately signed this specific structured data for this specific contract and chain in this specific format, and that signature cannot be replayed as a transaction across chains, across contracts, or across different struct types. You have now understood EIP-712 from first principles, every concept you derived through reasoning, not memorization. Now let's read the specification. Before we write a single line of code, I want you to read the actual EIP. Specifically read these sections: definition of hashStruct, definition of encodeType, definition of encodeData, definition of domain separator, specification of the each sign typed data JSON RPC. Your task as you read, write down in your own words, how does encodeType handle nested stubs? What is the rule for encoding dynamic types like string and bytes? What fields are optional in the domain separator and why? Come back with your answers and we'll start building EIP-712 verify and solve. So let us go to EIP-712. It is already opened. Definition of hashStruct. So here we have definition of hashStruct. The hashStruct function is defined as, what are these? S:(s) check 256 hash of type hash concatenated with the encoded data, where type hash, okay, so hashStruct is check 256 hash of type hash, which is check 256 hash of the struct name followed by the struct members concatenated with encode data s. Here s is the site data. Over. No, I don't know what s is. What s is. Let us check what s is. Here the type hash is a constant for a given struct type and does not need to be runtime computed. Okay, got it. So here it is. As I said, what is this S? The set of structured type data. S contains all the instances of all struct types. So that is this S. And what do we? Okay. Encode data S. What is this S? Type of S. Okay, S is nothing but a structure. Byte. For data where S is the structure. So this is hashStruct. Then definition of encodeType. Okay. The type of a struct is encoded as name concatenated with, okay, parenthesis, concatenated with member 1, concatenated with comma, member 2, and up to member n, where each member is written as type, concatenation, empty braces, concatenation name. For example, the above mail struct is encoded as, got it, encode type is simple. Encode type is KitChat 256 coded as name, encode type this example from our above discussion. So here we have struct transfer address to uint 256 amount. So that will be transfer address to uint 256 amount. So there will not be any space over here. So encode type is name, which is transfer, then that concatenated with the opening parenthesis. So here we have the opening parenthesis that concatenated with the member 1. This is the member 1 that concatenated with, then we have comma, then that concatenated with member 2. So here in our case member 2 is uint 256 amount. So this is a definition of encode type. Then what do we have? The next question is definition of encode data. Code data. The encoding of a struct instance is encode value 1, concatenate with encode value 2, concatenate with encode value n. That is the concatenation of the encoded member values in the order that they appear in the type. Each encoded member value is exactly 32 byte log. The atomic values are encoded as follows. Boolean false and true are encoded as uint 256 values 0 and 1. Addresses are encoded as uint 160. Integer values are sign extended to 256 bit and encoded in big Indian order. Bytes 1 to bytes 31 are arrays with a beginning index 0 and an end index length -1. They are 0 padded at the end to bytes 32 and encoded in beginning to end order. This corresponds to the encoding in ABI V1 and V2. The dynamic values bytes and string are encoded as KCHAC 256 hash of their contents. Okay. The array values are encoded as the KCHAC 256 hash of the concatenated encoded data of their contents. That is, the encoding of sum type 5 is identical to that of a struct containing 5 members of type sum. Okay, the struct values are encoded recursively as hashStruct value. This is undefined for cyclical data. The definition of encoded data is ENC value 1 concatenate value n. Okay. Encoded data is the definition. Then definition of domain separator. Definition of domain separator. Domain separator is equal to hashStruct EIP-712 domain, where the type of EIP-712 domain is a struct named EIP-712 domain with one or more of the below fields. So we have domain separator. So it is so I'm just copy pasting it, not string name, string version. Then we have event 256 chain ID. To that address, verifying contract. Then bytes 32 sort. Okay, as you read, write down in your own words, how does encodeType handle nested structs? EncodeType definition is recursive structs. I think it was given. Okay, this encode data. So the struct values are encoded recursively as hashStruct value. This is undefined for cyclical data. Okay, hashStruct. Okay, good. Definition of encode type. An example encoding is transaction person from person to asset. Asset is this, person is this. Okay. How does encodeType handle nested structs? It does not. It does not. Okay, got it. It handles nested structs. Here is the answer. If the struct type references other struct types, then the set of reference struct types is collected, sorted by name, and appended to the encoding. It handles nested structs by sorting it by name, and then appending it to the encoding. Example given in the specification talk is however, one thing to note is that it cannot handle cyclical structs. That is a struct referencing itself. What is the rule for encoding dynamic types like string and bytes? They are encoded as check 256 hash or data is the dynamic values bytes and string are encoded as hash of their contents. What fields are optional in the domain separator and why? So with one or more fields, protocol designers only need to include the fields that make sense for the signing domain. Unused fields are left out of the struct type. Okay. Name, version, chain ID. What fields are optional in the domain separator and why? As a type of struct, protocol designers only need to include the fields that make sense for the signing domain. Unused fields are left out of the struct type. String name, the user readable name, that is the name. Then version, the current major version of the signing domain. Chain ID, the user agent should refer signing it if it does not match the currently acting chain. Verifying contract, Byte 32 salt. The future extension to this standard can add new fields with new user agent behavior constraints. User agents are free to use the provided information to inform or warn users or refuse sign-in. DApp implementers should not add private fields. New fields should be proposed through the EIP process. Should be the order as above, skipping any absent fields. KF field should be the order as above, skipping any absent fields. Future field additions must be in alphabetical order and come after the above fields. User agents should accept fields in any order as specified by the EIP-712 domain type. What fields are optional in the domain separator and why? Name and sort. Because name is merely a cosmetic change that displays which DApp is asking your signature. Omitting it will not have any risks, and in case of salt, will after this, let me summarize this and we will stop here, and then in the next session we will build the EIP-712 verified bots. Encode data correct important details. He captured FB encoded values exactly 32 bytes. domainSeparator correct. Nested stubs correct. Good catch on cyclical structs being disallowed. Dynamic types correct. Optional fields partially correct. Let me push you on salt. You said you don't know why salt is optional. Think about it this way. If a protocol already has chain ID plus verifying contract plus name plus version, is there any remaining ambiguity about which signing domain you are in? So what problem would salt solve that the other fields don't already cover? Take a guess, then we'll summarize and close the session. If a protocol already has chain ID, verifying contract, name and version, is there any remaining ambiguity about which signing domain you are in? Put it. Salt will be a random value which is hard to guess and thus making the domain unique. Salt is a last resort uniqueness guarantee if two protocols somehow have identical name, version, chain ID and verifying contract. A random salt makes their domains distinct. It's also useful for protocols that want domain uniqueness without revealing their contract. So session summary. Here is everything you derived today mostly through your own reason. The problem EIP-712 solves: blind signing attacks, users signing opaque hex blobs controlled by attackers, ecrecover proves who signed, not what they understood they were signing. The 4 attack vectors EIP-712 prevents: cross-chain replay by chain ID, cross-contract replay by verifying contract, same action replay by Nonce in struct data, cross-format replay by using prefix x19 and x0. The 3 components of EIP-712 includes domain separator. It is static, cached once, identifies the DApp. It is stored inside a state variable. TypeHash, it identifies the struct shape, name plus field names plus field types. Encode data, the actual per transaction values, 32 byte each. The final hash is KChat256 hash, the prefix concatenated with the domain separator, concatenated with the hashStruct. YX19, outside all valid RLP byte range, can never be a transaction. YX01, version byte separating EIP-712 from other EIP-191 formats. Encode type for nested structs, sorted alphabetically, appended, no cyclical references allowed. Dynamic types, string and bytes are encoded as KChat256 hash of their context. So in the next session, we will build EIP-712 verifier.sol in this order. Encode type will give us the type hash, domain separator, hashStruct, verify using ecrecover and foundry tests. So come prepared with EIP-712 spec still open, Zeppelin EIP-712 implementation, read it but don't copy it, foundry installed and your copy trade vault repo ready. So yes, I hope by this you could say, using AI as your mentor and tutor, you too have learned what exactly EIP-712 is in depth. What are the different components of EIP-712? Why do we use a prefix? What is encodeType, encodeData, hashStruct, then typeHash, how typeHash is calculated. So having this understanding separates you from the average developers. So if you have learned something valuable, please do like, share and subscribe. Thank you.